during the COVID-19 pandemic. It's a very difficult time for us all, really. We are very fortunate in New Zealand that we have virtually eradicated it. We've had marvellous leadership from our government, and being a smaller country, I think, has made it easier for us to be more disciplined, you know, and so we're very fortunate. So let me share my screen with you. So the topic today is on multi-storey structure for gravity and earthquake loads. And this follows on from my previous lecture where I was talking about the structure for low-rise buildings. And as you will note, that many of the principles are the same. It doesn't really matter if you're designing a 3-storey building or a 13-storey building. The principles are actually the same. As we start to think about the structure for our architectural designs, we remember the key design criteria for designing the structure. The structure of our buildings must support the program, and hopefully the structure you design for every building will enhance your design concept. Remember, you're not designing the structure of your building for the contractor. You're designing the structure of your building to enhance and to express your concept. That is very, very important. So I'll just begin with a very brief comment about the structure you design to resist gravity loads. That structure consists of floor slabs, beams, and columns. And if at all possible, your columns should be continuous from the foundations to the roof. It is possible to stop some columns off at different floors, but if you stop a column, you've got to provide what we call a transfer beam. And that beam has to be approximately 2 to 3 times deeper than a normal beam because it's carrying the weight of a column. So it's best to avoid that and to make your columns continuous from ground level right up to the roof. In terms of the placement for your columns, you really should be thinking about the critical functional dimensions for your design. Like these might be rooms or office spaces. And so your building structure will be guided so that the structure does not intrude on any of those functional spaces. Excuse me, I'm just going to switch on my mouse. I think you can see my mouse now, is that right?
Yes, yes.
Great. So you start with your critical functional dimensions. I mean, like each of these could be, for example, like 3 or 4 car parks or 2 or 3 bedrooms in a hotel. And then between these critical functional dimensions, that is where you will place your vertical structure. So your columns, you know, will be placed outside the functional modules. And by doing that, your structure is not impeding, it is not affecting the function of your building. In some ways, it might be enhancing it. So this is quite a helpful way to think about how to decide where your gravity and earthquake resistant structure will go. Now I want to move on to the structure to resist your lateral loads, in other words, earthquakes. And before I really get into that, I want to show you once again and remind you of the seismicity of Indonesia and how you are living in a very seismic region. And once again, how every building you design has got to be able to withstand strong shaking in any direction. And so I'm just going to summarize the principles that I gave you for low-rise construction, because they apply just the same for a multi-storey building. So the first principle is that you've got to choose one of these structural systems for the direction along the building and one of those systems across your building. So in diagram A, along the building, 2 shear walls. Across the building, these 2 shear walls. For, if we're using moment frames here, we've got a moment frame along the building here and one on the other side of the building. And at each end of the building, and in fact, along the building, we have transverse moment frames. And so the key principle is one structural system for each direction, but you can have the same system in both directions. And then in my last lecture, I talked to you about the need to be able to withstand earthquake attack from any direction. So here's an earthquake pulse at an angle theta to the x-axis. Well, we can provide resistance against this force at an angle to the axis by providing resistance in the y direction and in the x direction. And so your job as an architect for every building you design is to make sure that you've got strength in the x direction, these 2 walls, plus strength in the y direction, these 2 walls. And these other columns, you'll need lots of other columns and beams probably, they will resist your gravity loads. You know, they will take the weight of your floor slabs and all the live loads in your buildings. But your earthquake loads can be resisted by these special elements that you will design. So there's the summary. We must provide resistance in 2 orthogonal directions in the building plan. Then the next principle is that in each direction, we must have a minimum of 2 structures. So like for this building, in the y direction, I've got 2 shear walls. And in the x direction, that wall and that wall. Note that this wall here is very weak in the x direction. Very, very weak. It will collapse. But it is strong in the y direction. And here I've designed a little building in using the Resist software here. In the y direction, we've got 2 moment frames, one on each side of the building. each frame has 2 bays. And in the X direction, we've got 2 shear walls, one there and one here. Now you will need other columns, or I will need other columns in this building to support the floor slabs. And these columns will be located according to those critical functional dimensions. Not only do we need a minimum of 2 structures in each direction, but they must be separated in plan. And so, like in the Y direction, there must be plenty of separation between these 2 shear walls, because that separation provides resistance against torsion, against the building twisting. And the same goes in the X direction. These 2 walls need that degree of separate, well, they don't need that much, but they need about 1/4 of this dimension separation to give that resistance against twisting. So that really is the summary of the principles that you need to apply for your designs. Now I'm going to, well, in a minute, demonstrate the Resist software that will help you utilize these principles and will enable you to do the preliminary design to dimension your structural elements for your design. And so I think you have been asked to download Resist, and I hope most of you have done that successfully. And that's what I'm going to demonstrate in a minute. But before I do, I just want to show you this building here, the Urha Clinic in Surabaya. I'm wondering if you know this building. Do you know it, Ibu Fenty?
Yeah, it's quite near with our campus, I think.
Oh, is it? Great.
I don't know whether there are any other RH clinic, but Ivan, RH clinic is only in
Mana saya tahu RH klinik, Ibu. Kalau nggak salah kalau di dekatnya apa di kampus itu kan apa ya namanya itu? Mungkin anak-anak di sini lebih paham deh kayaknya ini yang perempuan-perempuan.
So yeah, we noticed that there is a clinic near our campus, and I guess that it's RH clinic, but I don't know. Mungkin ada.
Well, I hope you don't need to go to it because it's a medical clinic. Here it is here. The designers are very proud of it because they submitted it for an international award. But I don't know if they were successful or not. There are other Urha clinics in other cities of Indonesia, I have discovered. But today, I'm going to redesign this clinic using the Resist software. And so, first of all, let's see how many stories there are. 1, 2, 3, 4. And just note that the story height seems quite high. It seems higher than a normal building. So we'll just remember that. And I think the clinic has a flat roof, and it has a cantilevered canopy at the front, but this is not connected to the main building. And it's got this light atrium, which is attached to the main structure. Here is a typical interior view. You can see it's very modern and quite attractive interior design. You can see the structural element. Here's a column Here's a beam. We can't really see too many other structural elements. Maybe that's a column there. But the rest, most of what we see is interior design elements. Then when we look at the plan of the building, this is the entrance canopy, which we can neglect in our design. And basically, I'm going to design this building here using resist. Now, let's look at the structure that is resisting, or let's look at the structure resisting the gravity loads first. So we can look in the plan, you know, and we can see columns that could support gravity loads. These walls will support gravity loads. You know, there are quite a few columns, aren't there, supporting gravity loads. Now, what about the structure resisting earthquake? Well, let's start in the Y direction, in this direction, the Y direction. Now, first of all, we've got these two possible shear walls. They could be designed to resist earthquake load in the Y direction, but they're quite short. And so I don't think they would have enough strength. And you've got tiny walls here that also would be too flimsy, too flexible to offer any resistance. What about moment frames in this building? Well, on each perimeter, you could have a moment frame. Like this is about 3 meters, roughly 3 meters. So you could have a column, another column here. That's about 6 meters there. And then about 6 meters to the column and then 3 meters there. So there could be a moment resisting frame along there and also along there to resist earthquake. This could be a moment resisting frame too, actually, because these columns are quite big. So we could have a 3-bay frame running through there with the bay lengths being different dimensions. And similarly, this could be a moment frame. But there's no other resistance in the Y direction. So for my design, I'm going to assume just 2 moment frames, one at each end of the building. What about the resistance in the X direction in this building? Well, we've got like one shear wall there. That wouldn't be enough because we need at least 2 structures in each direction. I mean, if we were going to use shear walls, we could have a shear wall there and, well, maybe a shear wall at the back of the building might be possible. And that could work for us. Or we could have a shear wall here and maybe, you know, one adjacent to the stairs here or here, because that could probably go the whole height of the building. I mean, I think that would be a really good place for shear wall there. Okay, so anyway, in my design using resist, I'm going to assume we've got a moment frame running along here and a moment frame running along here. You'll see that there's not a very good moment frame here because, like, see that column's quite big, and here you've got a really small column, and then you've got a larger column, large column, small column. Large, small, large. So it's not a very regular frame. And I would recommend that we would modify that to make it more regular and stronger. So this is the building we're going to design or redesign as an academic exercise. And so now I need to stop sharing and share my resist screen with you. Okay, so here we have the resist program now. I'll just switch on my mouse again. Okay. Okay, so first of all, this software is rule of thumb. It is not intended to be incredibly accurate. It's intended to give you the approximate dimensions of your structure that your engineer will refine and analyze accurately. But you will try and model your building, quite accurately. And as far as designing for earthquakes is concerned, one of the most important things is to model your building weight correctly, because the earthquake force is proportional to your building weight. So, first of all, we fill in all these fields. We start off by telling resist what type of importance our building has. Like if we're designing a hospital, it's about 80% stronger than a normal building. But for a private medical clinic, well, let's say it contains very high value contents, some like incredibly expensive medical equipment. So we'll click high value contents. That means that this building is going to be a bit stronger than a normal office building. Okay, how many stories has it got? 4. The story height? I don't know exactly, but I'm going to assume it's 4 meters story height. The roof height is very little, say 0.5 meter. Now we put in the weight of the floors, floor weight. Now the default option is a light floor. This is what a light floor looks like. It's wood. And so I don't think you would ever choose that. So our choice of floor is light, medium, or heavy. This is a medium floor with steel decking and a concrete slab. So you'd choose medium if you were using steel framing. But if you've got a reinforced concrete building, you would use heavy. So I believe most of the floors in Indonesia would be heavy. So you choose heavy. Now, it's really important that you make the right choice, because if you don't, your results will be wrong and your design could be dangerous or too conservative. What about the floor live load? Domestic for apartments, office loads, or storage, like for a library? Well, for this building, it would be office. Interior wall weights. Are the walls made out of brick, or are they made out of Gibraltar board? Are they heavy or light? Well, let's say that you've got some light walls and some heavy. So we'll go for medium. What about your exterior walls? Now, for this building we've seen, most of the exterior walls are glazed, but there is some brick exterior cladding. So I'm going to choose medium, which is probably being a wee bit conservative. And as far as the roof of the clinic is concerned, it'll have I think it'll have a heavy concrete roof probably. So heavy. There we are. Now we've defined the materials and the weights. The next thing we do is to continue to move along these tabs at the bottom. So we go to floor plan. Now this building is a rectangular, but it's more or less rectangular, and it's got it's about 40 meters. It's about 40 meters by 30 meters. And I do zoom to fit. Now, these walls here, they are the default structures, and I will be changing them in a minute, but I'll just put them on the perimeter at this stage, out of the way. Now the next task is to modify the shape of the floor plan to suit your design. And so I'm going to add complexity. I right click and I add points. And now I can drag and create the geometry of my design. And so you right click to add as many points as you want to create any shape of building plan. You know, you could design, you know, a really weird plan if you want to. And so you've got to model your design reasonably accurately. And you can do that by putting in lots of points and dragging. So this is more or less the plan of the Urha clinic. At the bottom of the floor plan editor, it's got the maximum dimensions and it's got the area. And so I should check that this area is close enough to the area of the actual clinic floor plan. And then I would know my design is going to be very accurate. Okay, so this is our building. You know, it looks like that, doesn't it? That we saw from the plan, more or less. Close enough. Now we go to the earthquake tab. And the first thing we do is we've got to choose the hazard factor. Now for Surabaya, I think it's going to be 0.3. So please, for your designs, you must change this to 0.3, which is suitable for Surabaya. For Yogyakarta, it's 0.4. For, say, Padang, it might be 0.5. It depends on your location in Indonesia. And like for New Zealand, you know, we have a map. And I mean, I live in Wellington, and its value is about 0.4, the hazard factor. Then you have to choose the soil type. Is your building located on rock, medium soil, soft soil, or very soft soil? The softer the soil, the greater the shaking and the more structure you need. So I will assume, I don't really know what the soils are like at Surabaya, but I'm going to assume it's on soft soil. Now Resist is able to design for earthquake. That's all we need to do. Next, we move on to the wind design. Now, in New Zealand, we have a wind map. Like this region is region A6 and so on. In Indonesia, you have quite low wind speeds. And also in Indonesia, your earthquake loads are always a lot more critical than wind loads. The only exception is if you're designing a timber building. And so usually you can neglect the wind load acting on your building because the earthquake forces will be far, far greater. So we won't worry about wind load. We move on to the structure in the X direction. So now we are going to design the structure in the X direction. We've got three choices. We can use structural walls, which is what we've already got. We can use moment frames, or we can use braced frames. You choose. As the designer, it's your choice. And you base your choice on those two criteria: program and your design concept. This is what a shear wall looks like. It's a pretty boring one with windows at the top. This is so if we go to shear walls, we can choose reinforced concrete, like that, or reinforced concrete masonry, which I think is rather rare in Indonesia, but it's like concrete blocks with reinforcement. Or if you're designing a timber building, you could use plywood shear walls, say for a low-rise timber building. The other option is to use braced frames, a timber braced frame, steel concentric braced frame, an eccentric braced frame, an inverted V braced frame, or tension only bracing, where the bracing elements are just very fine rods or even cables. And you see, there's Resist. I've told it I'm using a braced frame in the X direction. But actually, because we're designing this clinic, we're going to use moment frames. And so this is what moment frames look like. beams, rigid joints, columns, continuous. Reinforced moment frame. There's a steel moment frame in a steel building. See the rigid joints at every joint? It has to be incredibly strong. And then you can have timber moment frames where that's a rigid joint between the column and the rafter. So anyway, we are going to use reinforced concrete frames in this clinic because that's what's been used. So we're going to use moment frames, reinforced concrete, and I'm going to use two frames, one here and one here. So I'm going to go back to the floor plan and put this frame on that line. I mean, as a designer, we can put these frames anywhere we want to. It's entirely your decision as the designer. Okay, so this is the default frame that Resist gives us. Now I want to increase the number of bays. I'm going to have 6 bays. So the number of bays per frame at the moment is 2. See, they're just 2 bays. So if I click on this arrow, it's 3, 4, 5, 6. So now I've got a 6-bay frame here. And the bay length is 6 meters. I'm going to make it, say, 6.5. There. So it fits the building dimensions. So going back to our floor plan, that's one frame, that's the other moment frame. Now I'm asked, what is the floor width supported by the beam? So see these beams on this line, they are supporting some of this floor here. Like here you'll have more columns and beams supporting the floors of the clinic. And so say there's another beam and column here somewhere, say like about 8 meters away. Well, that means like 4 meters will be supported by these beams. So the floor width supported by this beam is going to be about 4 meters. So I've got to change that to make this more accurate. 4 meters. And finally, we've got to guess what the depth of the column is. Like this is the column depth here. Like in this rather terrible building, the column depth is more than 1 meter. Okay, more than 1 meter. At the moment, these columns are 0.3, 30 centimeters. And this frame is too weak, in my opinion. So I'm going to increase the column depth to say 0.5 meters. This is my guess. So this program is like trial and error. Now we go to the Y direction. And in the Y direction, we click on this tab. I'm going to use moment frames again. And I'm just going to use two frames because that suits the layout of the clinic. And I'm going to have, how many bays? I'm also going to have 6 bays in this direction. Oops, that's no good, is it? We can't have our bays outside our building. So I'm going to change my bay length well, actually, I'm going to change it to say 4 meters. No, that's a bit too close together. I'm not going to have 6 bays. I'm going to have fewer. I'm just going to have 4 bays. And 4 bays, and the bay length can be 6 meters. No, 5.5 meters. There we are. So go back to my floor plan editor, and I just drag that moment frame down, and I drag that moment frame down. Now just note that the frame, I can put the frame anywhere, the frames anywhere in plan to suit my design. Like I could have them there. But as I said before, for the clinic, it makes more sense to have the frames on the perimeter. So I'm going to do my design like that. Okay, so I go back to the Y direction. I've got 1, 2, 3, 4 frames. The floor width supported, I'll make that the same, 4 meters. And I'm going to increase my columns to make them stronger because they look too weak. I'm going to make them 60 centimeters. So now I've done my first design. Remember, there will be lots of columns and beams inside here to support the floor slabs inside, just like the real clinic that we saw. So now I've finished my first design. I put my hand on my heart and then I click results. Oh, because everywhere I see red, that means fail. So these bar graphs are for the wind load, which we can neglect. This is the results in the X direction for the moment frame. And so this is for the earthquake, the ultimate earthquake. This is for a small earthquake. But I've got to make sure that all my results are less than 100%. Now, the shear forces in my frame are 116% of what the code allows. Fail. The bending moments in my frame are 270% of what the code allows. Fail. The drift, that means the flexibility of the building. The drift means how much the building sways during an earthquake. That is 380% of what the code allows. So my building is far too flexible. So I've got 2 options. I can add more frames, but that is not a good decision because when we looked at the interior of the clinic, there weren't very many obvious areas for other frames. Or the other option is to increase the sizes of my beams and columns. That's the most economic choice. So I go back to the X direction and I increase my columns from 0.5 there to 0.9. And now these results are close enough. I mean, it's slightly failing, but not by much. And so there, our columns are a lot bigger now, but that is what we need for this heavy building on soft soils. Let me see now. So I finished my design in the X direction. Now let's go back to the results and look in the Y direction. The same problem. It's failing, isn't it, under the ultimate earthquake? It's too weak and it's too flexible. The drift is too much. So I just have to increase the sizes of the columns again. So I go to the Y direction. And I go from 0.6 meters column, and I just keep increasing it until it stops failing. There. Now my columns are really big, aren't they? 1.4 meters. They're a bit like the columns on this building. But remember, you've only got two lines of structure to resist all the earthquake in the Y direction. And that's why these columns are so large. The other reason the columns are so large is because we're on soft soil. If the building was on, say, medium soil, I go back to results. Now see how my results are they are less than 100%. So that means my design is too conservative. I've over-designed. So in the Y direction, if I discover I'm on medium soil, I can reduce my structural sizes. And see, now my columns are only 0.9, 90 centimeters, which is a lot more reasonable. So you can see that the soil conditions are quite sensitive. So let's just say we've done some more soil investigations. We know we're on medium soil, and therefore I can go back to the X direction and I can reduce the sizes of the members there. There we are, to 0.75 meters. So now I have done a complete design. My results are close to 100%, which means my design is very economical. And I finished my design. Before we finish the design, we look at other results. And it gives me some information about torsion resistance. And it tells me that the depth of my moment frame member is 750 millimeters, which is what I put in. And the width of the column will be 45 centimeters wide. And the beam dimensions will be 75 centimeters deep by, say, 40 centimeters wide. And so these are the dimensions you will show on your drawings. You know, this is the preliminary design you have done. There's information about the foundations, but normally you don't show that on architectural drawings, so don't worry about it. Now, once you've finished your design, then you should go to reports. But before you go to reports, you go to your 3D model and you rotate it so that you can see the structure really clearly. And if you want to, you can say switch off the roof to show it even more clearly. It's up to you. And then you click on this image and you click on set image for report. And now that image will be automatically printed out when you go to the reports page. Reports, you always choose architectural report, and you get a 2-page report with all your assumptions, like the floor, the weight type is heavy, and for example, the hazard factor is 0.3 and the soil is medium. And at the end of your report, there's a bit more information, and then you get a printout of the 3D model. Now we've done that successful design, I want to go back and see if we can use those 2 shear walls. So I'm going to go back, I'm going to go in the Y direction. And I'm going to see if I can use 2 structural walls. Sorry, it's wrong. It's in the X direction. So I go to the Y direction. I choose structural walls. I bring the walls into the, I go to the floor plan editor. I drag the walls in to where they are in the clinic. They're about there in the clinic. And then I go, I have to guess their length. I'm going to make them say 5 meters long and 25 centimeters thick. So that's my design. Look at the results. Okay, well, look, I've got 2 problems here. First of all, I've got this flashing red light. And I think you know what that means, don't you? It means danger. And second, you can see the walls are failing and drift. They're a bit too flexible. Okay, they're a bit too flexible. So let me solve the drift problem by making the wall a bit longer. There, 6 meters long, and the drift is okay. So you know, this is, I've almost finished my design. I go back to my report, my results, and see there's this flashing light. I click on it, and it says the lateral structure separation in the Y direction is only 25% of the building width. Adjust until it's greater than 25%. So what that is saying is that I've got to move these walls a bit further apart to get better torsional resistance. You see, if I move them too close together, I'll just get the warning that I haven't got enough separation. So if I want to use these walls as shear walls, I've got to move them out a bit wider than they are in the clinic. At the moment, they've separated 20%, 26% of the building plan. So look, if we could redesign the planning of the clinic to allow these walls to be separated a bit more widely, then we've done a perfectly good design. All our results are less than 100%. They're very close to 100%. And that tells us our design is very economical. And so there, I finished the design. I finished the design of the clinic using shear walls in the Y direction, 6 meters long, I think, and 2 moment frames in the X direction. One of you might say, well, look, Andrew, what if we want to use braced frames here instead of shear walls? Okay, we go to the Y direction. We choose braced frames. See the braced frames now? Each braced frame has 2 bays, which seems about right. The bay length, I'm going to reduce that, say, to 4 meters. The floor width supported will probably be more like 4 meters. The brace size, now I've got a choice of braces. I'm going to use eccentric bracing because that's the most economical. And my brace size is 20 centimeters. That's the size of the diagonal braces. Let's see what the results say. Here are the results here. The braces are failing. And so I've got to make the braces a bit bigger. There. If the braces are 25 centimeters, I've finished my design. And so that is another acceptable design for earthquake. So students, you can see that very quickly you can try out different structures to suit your design. Like in the Y direction, if I go back to the Y direction, I go back to moment frames. Let's say I'm going to have 4 moment frames. So I right click, put a moment frame there, and put a moment frame there. Now I've got 4 frames. I go to results. My results are very low. Therefore, I can reduce the dimensions of my columns and beams. And so originally my beams were 90 centimeters deep. I can reduce them. Now they are 75 centimeters deep. Okay. And it's up to me as the designer to make a decision on whether these frames can be integrated with the planning of the clinic or not. Just before I go, I just want to tell you that this advanced tab, please don't use that. That's just for civil engineers. And the displacements is just for civil engineers. So don't use those. And also in the help section, there's a tutorial to help you, a step-by-step guide. and information about the assumptions in the software. So all that information about the assumptions and guidance to help you model accurately is in the help section. So, Ebufenti, that's all I want to say. And I think now we're going to give the students time to do a resist model of their own design, aren't we?
Okay, thank you, Andrew. So, adik-adik, sekarang adalah waktunya untuk menggunakan resist. Jadi kemarin saya sudah meminta adik-adik untuk membawa desain PA, walaupun belum fix ya. Silahkan bisa digunakan dan dicoba dihitung dengan menggunakan resist software tadi. Nah, waktunya adalah 30 menit. So, we have 30 minutes for doing the projects. So after 30 minutes, then we will call you back and we will select students to present their works. So, jadi kalian harus ngerjainnya dalam waktu 30 menit. Nanti ada yang kami tunjuk untuk secara acak, kami akan tunjuk untuk mempresentasikan kerjaannya. Jadi selama mengerjakan, kalian boleh bertanya apabila ada pertanyaan atau ada yang tidak dipahami. Jadi seperti itu. Bisa dimulai sekarang. Apa ada pertanyaan terlebih dahulu? Nggak ada? Except for the one who... Ya?
Saya ingin bertanya. Sebelumnya saya Ananda Putri dari kelas B.
Iya, Nanda.
Kan di floor plan itu untuk apa namanya bisa diubah-ubah koordinatnya. Nah itu ada angka-angkanya kan di situ. Bu, saya nulis di chat aja kayaknya putus-putus.
Okay, so she's asking to draw the plan, I think, but she will try to type it down because her internet connection is not stable. But she's writing it down in the chat box now. Okay. Ada lagi yang lain? Ya, okay. Ada lagi yang lain mau nanya? Okay, we will call you back at 2:30, so 2:30. Then to start the presentation. Ya, silakan tadi Ananda ditulis dulu di chat box. I think for the one who are using Mac or Mac OS, you cannot use resist at the moment. So I think you can start to analyze your work and try to define which structure that you want to use in your design. So in case I choose you randomly, then you can just explain what kind of structure you want to use in your design. Because at the moment, the software is only available for Windows. I can use it on my Mac, but it's using a parallel OS. So I don't know whether you can install it, but it's a little bit complicated. So yeah, I think you can try to analyze your design and then try to input your structural elements that you want to use. Okay. All right, she is asking about the floor plan, Andrew, because it can be changed easily, but there is a number there, like number C 0.032 and so on. What is it about? Because she couldn't figure it out. Like, what is it about? The number in that.
Like the numbers that are changing.
No, I think the number in the blue and also in the red.
Yes,
yeah.
Yes, that's really a great question. The number in the blue is the coordinates of the center of mass of the building. The center of mass. The numbers in red are the coordinates of the center of resistance. Now, you don't need to worry about that as a student, really. But you want these 2 points to be fairly close together to avoid excessive torsion. Like if I put all my structure down this end of the building, see the center of resistance is moving to the left. And so now I've got a large eccentricity between the center of mass and the center of resistance. That's going to cause severe torsion. And so we want to have our structure more symmetrical.
Okay.
So is that okay?
Ananda, apa itu yang ditanyain atau yang lain? Ananda? Atau jangan-jangan ini, kamu nanya bikin denahnya? Atau gimana? Gimana nih Ananda? Where are you, Ananda? Wait a minute. Looking for her. Think she's writing down to respond. All right. Yeah. It's already answering her question.
Good, thank you.
Ya, ya. Oke. Baik, silakan adik-adik dilanjutkan mengerjakannya. Okay, Andrew, I think you can take a break for a moment or refill your tea. So that
Righto.
yeah.
So I'll come back in 20 minutes
Yeah, exactly.
at past.
Yeah.
Okay.
Yeah.
Actually, no, I'll come back in 10 minutes because there might be some questions.
Oh, yeah, right. Okay, thank you.
Okay, so
Yeah.
I'll be back in 10 minutes time.
Okay, thank you, Andrew.
Thank you.
Okay. Oke, baik. Silakan adik-adik. Kalau ada pertanyaan bisa disampaikan. Oh. Oh iya, ini kan biasanya lantai 1 sama lantai 2-nya kalau ada yang berbeda luasnya itu dipakai rata-rata ya luasnya. Jadi sistemnya seperti itu gitu. Karena ini sangat general. Jadi luasannya itu tadi diambil rata-rata gitu. Jadi bentuknya diambil yang geometri dasar aja.
Isi Bu, saya izin bertanya Bu.
Ya, silakan. Siapa ini yang nanya tadi?
Samson Bu.
Oh, Samson. Iya, silakan Samson.
Jadi kan bangunan saya itu ada kayak terdiri, kan ini rumah tumbuh nantinya punya tugas kita Bu. Jadi rumah saya itu nanti kayak ada kayak 3 bagian gitu Bu jadinya. Terus saya bikin 3, jadi kayak 3 struktur yang terpisah gitu Bu.
3.
Ini saya bikin 3 gitu atau kayak bisa salah satu bagian aja Bu?
3 struktur terpisah itu maksudnya ini, apa namanya,
Kayak,
masa kamu ada 3 gitu?
Iya.
Oke. Silakan diambil salah satu aja, Samson, yang paling besar ya.
Oke Bu. Terima kasih.
Oke.
Ibu, saya mau nanya Bu, hazard faktornya itu berapa ya Bu? Tadi kan soalnya beda-beda.
Ini tadi siapa yang nanya? Sebentar.
Kusnul Bu.
Oke, Kusnul. Kusnul, areanya di mana?
Kalimantan Timur.
Di Kalimantan Timur berarti sekitar 0, ya, gimana Pak? Ya, 0,5.
Sejak dengan Padang mungkin ya.
Iya, betul.
Oke Bu, terima kasih.
Hi, Bufenti.
Hi, Andrew. So we have questions actually. Wait a minute, I try to translate it. If we have a different massing on the first floor and the second floor, should we separate the model? I think it's related to the floor area, maybe.
Yeah.
Well, yeah.
No, we don't separate the model. We just take an average floor plate area. Just the average will be close enough.
Yeah.
That's a very good question. And this situation occurs commonly. So just take the average value.
Right. And then the next question is, wait a minute. If we use shear wall, then should we place the column in between of the shear wall on the X and Y, or there will be no column between the shear wall?
Can the student please share the screen?
Oh, right. It's actually a question from other lecturers.
Or can they draw a picture?
Oh, right. Pak Irfan, monggo Pak, kalau ingin digambarkan.
And if he could share his screen, then I can make a comment.
Yeah.
Because it's an interesting question, actually.
Yes. Oh, I think he's not here at the moment. Ah, right. Okay, maybe we can answer it later on. But students recently asked about the hazard factor of Kalimantan, right? Kusnul, yeah. Kusnul Kalimantan, yeah.
Iya, Bu.
Yeah, the hazard factor of Kalimantan, is it 0.5?
No. Let's look. Let me share my screen with you.
Okay.
And if we look at the earthquake map of Kalimantan,
Yeah.
you see it has very small earthquakes. So for Kalimantan, I think the hazard factor would be like you could use 0.
All right, 0.1. Yeah.
Quite low.
Yeah.
Because there's very little earthquake activity in Kalimantan.
Right. Okay.
Actually, maybe you could even use 0.5. Oh, no, sorry. 0. No, I think 0.1 would be sensible.
Okay, yeah. So basically, if we want to check the hazard factor, we can just use this map, right? Because you have mapped it.
No, look, you can't really. You've got to go to the Indonesian code.
Oh, right. Okay. Yeah.
Yeah, and in the Indonesian earthquake code, there is a far more accurate map.
Oh, okay.
The different zones.
Okay.
Yeah.
Okay. I think we will have a little more minutes to go before I select one of you to present your work. Oh no, two of you. Okay, now the time is up, but you can still work on that while your friend is presenting. So I will select from the one who did not turn on the camera. And then suddenly everyone is turning on the camera. It's always happening. Okay. I will ask, wait a minute. Wait a minute. Nurma Fatia. Nurma Fatia. Nurma Fatia. I cannot hear your voice. Nurma Fatia, saya belum dengar suaranya. Tapi ada bunyi tik 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 tik. Nurma Fatia. Aduh, kemana nih? Okay. Let's change to another student then. Maybe her microphone is not working. Anisha Chandra. Then. Anisha ini janjiannya yang pakai mic tadi. Anisha? No, we cannot hear you. Oh, no. Anissa kok hilang juga tadi Anissa? Kok hilang dia ya, Anissa? Halo? Where are you? Okay, next students. It's getting harder. I think Syahla. You can show your work, even though it's not finished. Gak apa-apa.
Tunggu sebentar ya, Bu. Saya tadi nyoba-nyoba jadi ini lagi.
Gak apa.
Okay, it's not really good though.
It's okay. Yeah.
Okay. Good afternoon, Mr. Andrew. This is my result. This is the 3D model. It's 2-story height. Each floor. Each floor has 3.5 story height. The number story is 2. The roof height is 2 meters. I have a timber wood structure, and then the floor weight is heavy because I'm using precast flooring with topping, and
Yeah, very good.
Yeah, and then the floor lift load is domestic because it's a home. The interior wall weight is light. Actually, I'm still not really quite understand the difference between these two. Maybe because of my vocabulary, and then the exterior wall weight is medium because it's combining between the light and the heavy, and the roof weight is light because I'm using the the timber or wood structure. The floor plan, I don't know if it's right or not. This is my floor plan.
Yeah.
And then I placed in the lateral structure, the axis is moment frames because I'm gonna place some windows and doors there. The number base, it's because of my design concept. I am using 2 bays. The bay length is 5 meters, and the floor width supported by beam is 3 meters. But I'm still not quite sure about this one because I'm just guessing. The column depth is 0.35 because it's trial and error. And for the y-axis, I'm using structural walls because it's not really important here to have windows because it's next to it is the neighbor.
Oh, yes.
House.
Yeah. Very good thinking. Excellent thinking.
Yeah, and then the wall length is 2 meters. I'm still when I got called by Miss Fenty, I was still trial and error, still trying guessing the wall length. So I'm using 2 meters, and the wall thickness is 25 centimeters because I don't want it to be too big for the interior later. And the earthquake, I'm guessing in Bandung, is 0.5 hazard factor, and I'm still not quite sure about the soft soil and the medium soil, but I'm choosing the medium soil for now.
Yeah.
And then the result is this. Yeah, the shear. There's I don't know if it's good. If it's not, it's so far from 100%. Is it good or not?
Well, let me comment. If I'm just having trouble. Oh, here we are.
Okay.
Your maximum value in the X direction. Oh no, sorry. I think I haven't got your screen again.
Wait.
Yeah. Let's go back again.
Oh yes, look, I'll tell you, because in the X direction, you're using steel moment frame.
Wait.
Anyone?
Oh yeah, steel moment frame.
Do you really mean steel, or why don't you use the more common reinforced concrete?
Because it is failing.
Oh well, you just make the columns a bit deeper.
Deeper, okay.
See, there you are. That's close enough.
Yeah. Let me see the floor plan. Oh yeah.
And in the Y direction, your drift is getting close to 100%, which means that you've got a very economic design. You know, you can't make those walls any shorter than 2 meters. Otherwise, your structure will be too flexible.
Oh, okay.
So look, you've done a very nice design for that house.
Thank you, but still a bit fail.
Could I just say, actually for Bandung, I think the hazard factor is probably more like 0.3.
Oh, okay.
So
let's reduce it.
Yeah. So now you can even reduce your columns and make them smaller.
Okay, that's good. Thank you, Mr. Andrew.
So look, congratulations. That's a lovely little design you've done. And you could print out your structural report and show it to your tutor as proof that your design is safe.
Wonderful. Thank you, Mr. Andrew. Yay.
Well done, Shahla. Thank you, Shahla. I think I will ask Andrew about the question previously I mentioned. Wait a minute, I will open the image. So, this one here. So, can you see the image now?
I can.
Yeah, so the question is, if we use the shear wall on the edge side, so here and here, so
Yeah.
do we need to have a column in between like this image?
It's up to you. I mean, normally you would have columns to reduce the span of your beams for gravity loads.
Right.
So normally there'll be lots of columns like those blue columns, I say, to reduce the depth of your beams.
Oh, right. Oh, yeah.
You know, the beams for gravity load.
Yeah. Okay,
That's
thank
right.
you. Yeah. Okay, thank you, Andrew. So we have one more student, or should we continue?
Well, let's have one more student. It's really fun looking at nice student work.
Right, okay. So next students, I think Ahmad Faza. Okay, you can share your work.
Okay, yeah, I'm going to share my work. Okay. Can you see my screen?
I can, thank you.
Okay, so yeah, good afternoon. So this is my building that I designed for my studio. So the shape of my site location is actually like this. So it's not rectangle, or well, it has a little bit of a shift here and there, so that the shape is yeah, as you can see in my screen.
Yeah, that's
so,
just fine.
Then yeah, it's a 2-story building with 4-meter height in each story, and the roof height is 2.2 meters. This is just a rough guess because I still don't know how high my roof will be. And the floor weight is medium. So for the floor life load,
Excuse me, I just want to ask about the floor weight.
Yes.
Does this mean you are using steel structure in your building?
No, I'm using concrete slab, I believe.
Okay, well that should be heavy then.
Oh.
It must be heavy.
Okay, yeah. Thank you for the correction.
That's okay.
So,
regarding the
yeah.
live load, what is the purpose of this building?
Okay, so the first floor of my building is a house. It's a place. It's a house for a family, and the second story is for an architect studio with probably 10 people working there at the same time.
Okay, well you've chosen office, and
yeah, that's why I choose office as the
well
live
done.
load.
Yeah, that's correct.
And then for the interior wall, I'm not sure if this is correct, but I choose light because it says it's the usual choice. And then for the exterior, I use medium, and the roof weight, I use medium. So my exterior wall, yeah, I think it suits with the definition here.
A medium roof assumes a tiled roof.
Yeah.
Is that okay?
Yes.
Yeah, I think it is the common thing that students use. Kamu
Yep,
pakai ini ya,
that's-
tile? Faza? Pakai
Actually, I use what is it? A modular apa rumput gitu Bu Fendi untuk roofnya.
Oh, right. Oh,
What is it
green.
in English?
Is it
Jadi
green roof? Is it
green.
yeah, it is.
Ah,
Oh, well, if you've got a green roof, that's going to be very heavy.
so you put
Oh,
it
it's
heavy.
okay.
Yeah. Andrew, I
Wow,
think
a lot of wrong shapes
That's
here.
okay. That's okay. This is normal to do corrections.
Okay.
yeah, Andrew, I
All
think
right.
students need
Yeah, I believe my
explanation.
result will be failing all over the place.
Okay, so I think students need more explanation related to the interior
Oh, no, sorry, I'm
walls.
lagging.
Interior walls. I think the light and the medium and then the heavy, because usually in 2 stories building in Indonesia we have the same type of walls, exterior and interior. So what is the difference between light, medium, and heavy?
Well, a light interior wall would be using timber or steel framing with Gibraltar linings. In other words, for light walls, you would not use any bricks at all.
Ah, okay.
But if you're using bricks, and just some of your walls are bricks, then it would be medium. And if all of your interior walls are bricks, then it would be heavy.
Oh, okay. Yeah. So I think light is more partition. So students, if you know partitions from gypsum, usually you know that gypsum. Kalian pernah tahu dinding gypsum yang diketok-ketok itu dengar?
Ya, Bu.
Nah, itu yang light.
Yes.
Correct.
Ya, so the medium itu kalau separuhnya pakai itu sama separuhnya pakai bata. Jadi ada kombinasi antara itu. Kemudian yang kalau kayak biasanya kalian pakai batu bata semuanya itu masuk yang heavy. Gitu. But it's okay. I've just discovered it yet. Saya juga baru tahu gitu. So that's okay. I'm learning at the moment. Okay.
Can you show me your earthquake input, please? The earthquake tab.
Okay.
Okay, so you're assuming building in Surabaya, are you, on soft soil?
Yes. Yeah, it's actually close to Surabaya. I see.
Okay, perfect.
Close to Surabaya.
Yeah, perfect. Okay. And just show me your results again, please. Your results.
Result. Yep, it's failing a little bit.
Okay, so
Because of the changes.
Increase your column sizes. There you go, it's close enough. Yeah, 0.5 is close enough. Okay, and then go to your walls. Oh, no, I noticed that you're using
walls
in the Y direction. I see that you're using your reinforced concrete masonry walls. So are you using concrete blocks?
Yes.
Reinforcement inside.
Honestly, I don't really know the difference between two of these, but this seems more, I don't know.
Well, you can either use reinforced
I don't really know the difference.
or reinforced concrete masonry. I think for this exercise, just go to reinforced concrete.
Okay.
And so you've got two walls and your percentages are quite low. So you could reduce the wall length.
No, the wall length. No.
Oh, okay.
Yeah, there you are.
Yeah.
It's perfect, 2.5 meters. So there you finished your design, okay? Congratulations. You've got a nice design and you finished it.
Okay. Okay.
Okay,
Thank
you, Faza. Okay. Okay, Andrew, you can continue to your lecture.
Righto. Well, well done, you two students. You did a nice job. So now I just finished my lecture. I'm going to share my screen again with you. And now I'm going to talk about the configuration of buildings, the vertical configuration. Because even if we have used the Resist software to do a design, we still have two types of irregularities we must avoid. The most serious is called the soft story, and the second is called the short column irregularity. And so you have got to check your designs that you haven't got one of these happening. And I'm going to explain what they are and give you some solutions. So the definition of a soft story is where your columns are weaker than the beams if you're using moment frames. And or where one floor or story of your building is more flexible or weaker than a floor above. That will generate a dangerous soft story. Here's some examples of soft stories. An open ground floor with infills above. So the infills make the upper floors stronger than the lower floor. So in an earthquake, this lower story would get badly damaged. In this building, the lower floor is a soft story because the column height is greater than the stories above. And so these columns are a lot more flexible than the columns above because these columns are longer. Therefore, this is going to be a soft story and it is potentially dangerous. In this building, notice how the middle column, it doesn't continue. And so this is creating a soft story because at this level, we just have two columns on this frame and above we have three columns. So this will be soft. In a soft story building, we usually have weak columns and strong beams. And so the damage occurs at this level where the columns lean over and get damaged. When we're using moment frames, we want to use a safe design. I'm sorry, I haven't got my mouse going. In a safe design, we want to have strong columns and weaker beams so that during an earthquake, the damage occurs throughout the whole building and not just at one story. Like in this building, these black dots are the damage to the columns. And so we want to distribute the damage throughout the whole building so that the columns don't get badly damaged and won't collapse. That is our goal. Here's a building that will be a soft story. It's open at the ground floor. The beams are very strong because they've got masonry on top of them, and the columns, are relatively weak and flexible. Here's a building, here are buildings, 2 buildings in India that have lost their ground floor in an earthquake. The ground floor has collapsed here and here because probably there was car parking under here, and above there's lots of partition walls to make the building very strong. Like, look at this wall here. It isn't even damaged. It's very strong, but underneath it there were just columns. Here's another building where the ground floor has disappeared because of a soft story. Originally before the earthquake, there'd just be columns underneath this building. But you can see that above, the columns are infilled with partition walls that make it very stiff and strong. And so the soft story was just so weak that it collapsed. And here are other buildings. In each case, the ground story is soft, and that is where the damage has been concentrated. This building has collapsed and it's crushed the cars parking underneath it. So soft stories are very dangerous. Now, if you have a soft story when one story is higher than another, then you must use shear walls to resist the earthquake force. And I'm sorry, you cannot use moment frames because the moment frames will form a soft story. But if you use shear walls, they do not suffer from a soft story situation. So if you have a building with a very high ground floor, then immediately you should be using shear walls to resist earthquake. And you can use columns and beams to resist gravity. That's no problem. But to resist your earthquake forces, you have to use shear walls. What about short columns? This is the second common deficiency for vertical configuration. A short column is usually a normal column that is shortened by the presence of infill walls. And if a column is like captive due to infill walls, it becomes shorter. Its effective length is only this much. And the problem with short columns is that in an earthquake, they snap like carrots. They're too short to bend. And so short columns in an earthquake, they always show 45-degree diagonal cracks as a result of a shear failure. Here are a couple of short columns in a building in Indonesia that I visited after an earthquake. You can see where the 45-degree cracks were, and all the concrete has disappeared from these short columns. It's a wonder the building is still standing. So how do we solve short columns? This is the problem. You have infill walls, making the columns really short, just here and here. How to solve that? how to avoid those short columns? Well, the best way is to separate the infills, to provide physical separation gaps, so that during an earthquake, the columns can bend over their whole length, their whole height. That's a really good solution. Now, if we use structural walls, we just have to be careful about penetrations. Here's a wall I designed many, many years ago. It's a shear wall. It was retrofitting this telephone exchange. But the windows had to be at the top of the building. We couldn't have windows at the bottom in the shear wall because the stresses were too great. And so when you have a shear wall, you've got to be very careful about the penetrations. And resist actually tells you if you can have penetrations, if you look at the other results in resist. But like here's a shear wall here. This is a building from Chile, actually. And look at this terrible penetration, weakening the wall. And so, you know, these penetrations just cause so much weakness to make these walls very dangerous. Look at that penetration. So be very careful with penetrations near the bases of any shear walls. Now onto horizontal configuration. A few comments about that. We're going to look at this building. This is a plan view. In the Y direction, we've got two structural walls. And in the X direction, we've got a 2-bay moment frame there and a 2-bay moment frame there. The column depths are rather exaggerated. Now, during an earthquake, these are the inertia forces that occur during the shaking. Wherever there is mass in a building, during the shaking, there will be inertia forces. And so in section, you can see the way the building is drifting. You can see the deflection, you know, at this level. That's the deflection. And you can see these inertia forces that are acting in section. Now, if we look at this floor in plan, we see this. Here are the two shear walls at each end. And here are all the inertia forces from the weight of the columns and beams, from the weight of the floor slab, causing these inertia forces. And so the inertia forces, they have to be transferred horizontally into the shear walls. Then our building is safe. So the floor slab, it has to act like a horizontal beam, resisting these inertia forces and transferring them sideways into the shear walls. The floor acts like a beam, like a horizontal beam, spanning in the horizontal direction. And it has a deflection in it, depending on the length of the span and the size of these inertia forces. So here is a similar diagram. Here the shear walls are. Here are the inertia forces. And so if I draw the floor slab as a beam, that's the beam, the floor slab. Here are the inertia forces acting on it. Here is the deflected shape of the beam between the two supports, which are the shear walls. This is the shear force diagram in the floor slab. And this is the bending moments in the diaphragm. And so as you'd expect, the maximum bending moment is at mid-span of a diaphragm. And so the further apart in plan the vertical structure, the stronger the diaphragm must be. So like if this distance is like 10 meters, then the diaphragm doesn't need to be very strong. But if this is like 40 meters long, then the diaphragm has to be very strong because the shear forces will be great and the bending moments will be great. Now, we've got to be very careful as architects about the penetrations in diaphragms, because remember, during an earthquake, a floor diaphragm is a horizontal beam. And so if you put a big notch into a beam, you destroy it. It'll break. However, if you carry a beam along the edge of your floor diaphragm, then you can withstand the bending moments here, and this penetration is acceptable. It's okay. What about if you have a penetration near the end of your floor slab? Well, this is quite dangerous, really, because the inertia forces want to try and get into the shear wall, but they can't because this is an opening. So they try and go through these two areas that will probably break because they're not strong enough. So this is not a good design. And this is the best location for penetration, in the middle of your floor slab, because there the shear force is the least and the bending moments can be carried in tension and compression by the beams supporting your floor slab. So this is dangerous. This is okay. This is best. And this is dangerous. So be very careful about the penetrations you provide in your floor slabs, which we also call diaphragms. The next type of issue regarding horizontal configuration are reentrant corners. This is a reentrant corner. This building has 2 reentrant corners. This one has 4. 1, 2, 3, 4 reentrant corners. And this has 4. 1, 2, 3, 4. Why are reentrant corners dangerous? Well, here's a building with 1 reentrant corner here. If the building has shaking in this direction, this wing of the building, it will shake more vigorously than the rest of the building. And what happens is we tend to get damage to our diaphragms in this area. And remember that often in this area, we want to have penetrations for stairs and for elevators. So this is a weak area anyway. So, but it's this wing, it like flaps around like the wing of a bird. And so that is why re-entrant corners are quite bad. So what do we do if you want to have a building with this form? The answer is quite simple. You provide a separation gap. So you separate this part of the building from this wing. And your building now consists of two separated structures, separated by a seismic separation gap. The width of this gap depends on the flexibility and the height of your buildings or of your building. And the gap could range from, say, 10 centimeters to, say, 60 centimeters, depending on the height of your building. If you want more information, you've got to look at my book, Seismic Design for Architects. And that tells you how to calculate the width of the seismic separation gap. In the lower building, what we would do in practice is we've got one building here. We would require two separation gaps. And so now we would have one building with three separated structures. Each structure has to have resistance in the Y direction and the X direction. And by doing this, we avoid re-entrant corners. And this is what practicing architects do. They provide these seismic separation gaps to avoid the re-entrant corner. So in summary, when it comes to designing a floor slab or a roof slab of a building, during an earthquake, that floor or roof slab has to function as a diaphragm. It's got to transfer the horizontal forces into the vertical elements where they can go safely down to the foundations. The other way of thinking about your floor slabs or diaphragms is to think of them as they must tie your building together. You don't want your building falling apart during an earthquake. You want it to be tied together and move so that each floor moves together. Like this floor moves as a single unit during the shaking. It doesn't break apart and move in different directions and causing the building to collapse. And so each of your floor slabs should tie your building together and make that floor move as a single strong unit. If you've got large penetrations in your floor slabs that mean that you can't tie your building together, then you need to create separate structures in your building using seismic separation gaps. That's the strategy that we would normally adopt. Now, getting very close to the end of my lecture, I want to introduce you to the topic of pounding. This is what happens when buildings pound each other. They vibrate, they don't vibrate in phase like this during an earthquake, but they vibrate out of phase and they hit each other. And you can see the terrible damage that's been done to the building on the right, where it's pounded against the building on the left. I mean, this damage is really severe. I mean, people will have got killed during this earthquake. And probably that pounding has damaged this building. You can see damage to the beams, can't you, of this building. Quite a lot of damage is visible. So how do we as architects stop buildings pounding each other? In principle, it's very simple. Here's an elevation of a building. We must have a gap, a seismic gap between our building and the boundary, so that during an earthquake, as our building sways, as it moves to and fro, the top of our building must not cross the boundary line, because otherwise it could pound the neighbor's building. So in plan, it looks like this. Here's our building in plan. This is the street. Here are the boundary lines. We've got to have the separation, this gap between the sides of our building and our boundary, so that we won't hit our neighbor's building during an earthquake. What is the size of this gap? The size of this gap depends on the height of your building and the flexibility of your building. You will have to ask your engineer what that gap must be in order to avoid pounding. But in practice, this gap can be anywhere between, say, 5 centimeters for a low-rise building to, say, 60 centimeters for a high-rise building. This is the size of gap that we must provide to stop pounding. If you need more information than I've given you in this lecture, you can find all the answers in this book, Seismic Design for Architects, Outwitting the Quake. And I hope that your library, your university library, it might have an electronic copy of this book, because if it does, then you can easily, open up the book from your home computer and get the information you require. And so that is the end of my lecture. And so, Ibu Fenty, I suggest we invite the students to ask any questions about my lecture. And then if we have some time left over, we can go back and look at some of the other students' resist designs.
Oke, thank you Andrew. Silakan adik-adik apabila ada pertanyaan bisa raise hand atau ditulis di chat box. Baik, oke, ini ada yang sudah raise hand. Silakan, Kang Bagus dulu.
Thank you for the time. Sir, I have a question about the short column problem.
Yes.
Can you provide an example on the gaps for between the infills and the columns, like the materials to use for the gaps, because I can't really visualize it in my head. Thank you.
Yeah, thank you. That's such a great question. And I mean, it's so relevant to architects. I'll just go back. Oh. Okay, I'll just share my screen again. So I need to just go back and find that slide. Yeah, so the gap here, it depends, the thickness of the gap, it depends on the flexibility of your moment frame. But typically, these gaps are between 2 centimeters and 4 centimeters wide, typically. And so you create the gap and then you would fill it with polystyrene, or maybe you would fill it with a fire-resistant fibrous material. And then you could apply sealant to cover the gap and make it, waterproof. Or you could cover the gap with some type of metal flashing, seam. And so those are the normal ways that architects deal with these gaps. You require them to be filled with soft material that will squeeze as the column bends over towards the wall. And then, you need a sealant or metal flashings to create a nice finish over the gap. Of course, the sealant is soft, compressible sealant. You'll notice that if we put these vertical gaps, then the infill walls can very easily fall. They become very unstable. And so you'll notice that we provide some steel fixings in the corners of the wall, sort of like this. So the wall can move like that, but it can't fall in and out of the building. And so in my book, I give the details of these fixings, but I'm not showing you today because, well, I haven't got the time. So look, thank you for your question. That's a brilliant question. Are there any other questions about these avoiding short columns?
I think from me, that's all. I think that's
okay. Thank you very much. A very good question.
Okay. Then, Sharla, you have raised your hand before. Is it already? Do you have the same question?
Tunggu sebentar, Bu.
Okay.
Boleh Ibu langsung aja nanya.
Okay, boleh. Yeah.
Okay. Hello, Mr. Andrew. I will ask about my studio project task, and so I want to screen my plan. Okay, thank you. My plan is not really that it's quite bad. So it's I have a so yeah, the issue is I have 2 split level in my design. This is the first one, and this is the second one, and then next to the second floor. And then what I want to ask is the split level is quite high from the elevation, the 0.0 elevation. From this second split level is the floor height from the ground is 2 meters, and the lecturer said that the maximum height from your top of your foundation to the floor is 1.25 meters height. So I'm planning to have the ground to be rekayasa itu apa ya, Bu? Rekayasa tapak.
Modification?
Yeah, modification. So I want to make the ground a bit higher in here, and my lecturer said that you can still using the same foundation with the front structure here, but you treat the walls here differently because it is inside the ground. But I'm still not quite sure if I want to do that, or I'm just modify the ground.
Modify the ground. Yeah.
Dibikin apa, Bu? Kayak slope gitu, Bu, slope. I want to make it like a slope.
Okay.
Yeah. What's the better option for me if I have this two split level? Thank you, Mr. Andrew. I'm sorry if it's not
Okay,
quite.
well, the first thing I would like to observe is that at your first floor here, you have not got a split level, have you? This is a constant level. And is that correct?
Yeah, this one is oh yeah.
This is the lower level here.
Yeah. Yes.
Yeah. So the good news for you is that you can tie your building together with a good diaphragm, same level at this level here. And also at your roof level, you need to tie your roof together and make it a diaphragm. And your roof is at the same level, more or less. So that's good as well. Now, what you propose here, I think is okay. And so, yes, you have your foundations, raise your foundations and your floor slab to these levels. I don't see that as a problem. But what it means is that your columns and walls at this end of the building are going to be quite a bit higher than your columns and walls here, aren't they?
In here.
But so this wall here, can you show me your floor plan?
And
wait.
You can use the annotation perhaps.
Oh, yeah, sorry. Let me see if I can annotate it. Are you okay?
Yeah.
I will draw.
Jangan gerak-gerak dulu.
Oh, maaf.
Oh yeah.
Sorry.
Yeah, so these walls are a lot higher than the walls at the back, aren't they?
Yes.
These walls are a lot higher and more flexible. So let's look at how you are resisting earthquake force in this direction. Now I can see plenty of walls like here's a wall here. Here's a wall here. Does this wall continue up the height of your building or not?
Yes.
Okay. Does this wall continue up the height of your building?
Wait. Let me say this one.
From ground floor.
This
This wall does. Okay.
This one is not the middle one. The between this is not. I'm not taking it to the above ground. Above. Yeah.
So we need to remove. Could you please erase that wall?
Okay.
Thank you.
Yeah.
And can you erase this wall, because this is not a strong structural wall here.
In the back or in the front? At
the front wall. Actually, I can do that.
Okay.
Oh, you've done it. Okay. So I'm going to draw. Oh. So at the moment, your building, for earthquake in the X direction, you've got walls here, here, and here, but you haven't got any walls at the front, have you?
Yeah, I'm not yet.
Not
My
yet.
plan is still not quite fixed. Yeah.
Okay, well, I think you need some strength at the front here. You need a good bracing wall of confined masonry with a small window there. That would be okay.
Okay.
So annotate. So let's say you have a bracing wall there. So now I think the house has enough bracing in the X direction. What about in the Y direction? Can you please show me the walls that can go from the foundation to the roof?
Okay. This one.
Perfect.
This one too. Also this one. There's a lot actually. Can I place here?
Look, I think you've got enough. I don't think you need any more.
Okay.
So I think in the Y direction, you've got 1, 2, 3, 4 walls. I think that's great.
Okay.
So look, I think your design, in my opinion, is really good. So well done.
Thank you, Mr. Andrew. That is
It's
nice.
okay.
Okay. That's all my question. Thank you for clearing up. Okay.
Very good.
Thank you.
Okay, thank you, Shahla. Is there any more questions? Okay, Rido, silakan.
Apa suara saya terdengar?
Ya, dengar.
So, Mr. Andrew, I just wanted to ask a question for soft story. I mean, is there any prevention measure or a rule of thumb for building rigidity, which against soft stories in earthquake-resistant design, or is it just shortening column height? While, but what if the ground level are for the car parking purposes that requires the greater columns? I mean, the higher columns than the upper level, or maybe is there any other option?
Yeah, I mean, that's a really good question. So I'm sorry, I'm terrible at drawing with my mouse.
Yeah, it happens to me as well.
So say you're designing a building like this with a high ground floor. So for an earthquake, this becomes a soft story. So there are actually two options. What you could do is you could put beams through here, but no floor slab. Just beams on the perimeter of your building. And now you've got like a regular frame. But if you can't or don't want to do that, then you have to use shear walls. And so in plan, you know, you will put it, say, like a shear wall there in the X direction, say a shear wall there, a shear wall here in the Y direction, and maybe, you know, maybe a shear wall there in the Y direction. And then all your columns, they can be high. So you can have this, but like this might be shear wall here. Like there's your shear wall. But this is open. And here are your columns. Here. So if you're going to have a high level for parking or a foyer for a hotel or something, then sure, you can have that, but you've got to use shear walls. And so here's the shear wall, and it'll have, you know, a strong foundation beam, and it'll probably have tension piles underneath it. So that is the normal solution to solving a soft story. Don't use moment frames, use shear walls to resist earthquake. Do you want to ask a further question?
Sudah jelas? Siapa tadi saya?
Sudah.
Okay, so it's clear enough, Andrew.
Okay.
Yeah.
That's a great question. Well done.
Okay. Okay, I think we've reached almost, we almost finished the class. I think it's okay, Andrew. We have very comprehensive lecture from you, and then also you have seen some students, and I'm glad that one of the students asked their design as well. So
yeah, that's great.
yeah, it's really nice to hear that they can combine what they learned today to their studio, which is really good. I think I would like to say thank you, Andrew, for coming for the second time. And we will be expecting you the next time for the last lecture for these courses. So thank you so much, and I hope you a very beautiful day and have a good sleep after this, because it's been very night there. But before that, I will explain a little bit about students' assignment for next week. But if you want to leave the forum first, then it's fine for you to leave. But if you want to follow us until the end, it's okay. So it's
okay. Yeah.
Yeah, it's
Look,
okay.
I think I will leave, and I look forward to. I will look forward to seeing you all in my next lecture.
Yeah. Okay. Thank you, Andrew. Bye bye.
Oh, before I do, could I say that, like, for the next lecture, I would like to see more student designs with the resist reports.
Ah, right. Okay. Okay then. Yeah.
And so I want all the students to complete their resist modeling with the resist reports. We can look at a number of examples after my next lecture.
Yeah.
Okay.
Ya.
Goodbye, everybody.
Bye, Andrew. Oke, baik. Adik-adik, saya akan menjelaskan tentang soal lagi. Sebentar, saya stop dulu ya recordingnya.